Assalamualaikum guys, I am Hafsa Arif and this is our fifth lecture about DSP, Digital Signal Processing. In the previous lecture we have studied about discrete Fourier Transform. Now we are going towards fast Fourier Transform. First of all we are going to look at some background. In the first lecture I told you that we have sometimes we have unsorted data and sorted data. In unsorted data we do linear search and in sorted data we do binary search. While doing linear search, the worst case was n, when we reach our results after doing n iterations, and in the binary search our result was log 2n, and that is a smaller value. Let's say we have taken an example that we have n is equal to 5. In unsorted data and linear search we are going to have the worst case at 5 iterations, but in this case in binary search we are going to have the result in almost 2 or 3 iterations. So this is much less than this iteration. And if we go into larger terms, in very large terms, let's say if we have this like a very large term, so its log will be very smaller than this thing. Okay, then what's our goal? We need to reduce number of iterations and worst case factor. And also while doing DFT, what we have done in DFT, we had some x of n and we converted it into x of k by doing this summation and this multiplication. So when we do this summation, we do n minus 1 into n additions and we do n into n multiplications. Now computers do additions. So it is easy for a computer to do multiple additions instead of multiplications. And we also know that one multiplication is approximately equal to 25 additions. So you can see that if we are doing one multiplication, we can easily do 25 additions in that capacity of the computer also. So what is our goal now? Our goal is to reduce multiplication. The much we will reduce the multiplication, the much our cost factor will be low, and the much we will need a low speed computer. Okay, here we can see that if our n is equal to this term, our addition would be 2.5 into 10 raised to the power 23, and our multiplication would also be 2.5 into 10 raised to the power 23. So we want to reduce these multiplications even if our additions are being increased. There is no issue in increasing addition because computers do additions. Okay, then to reduce cost we are going to use a technique that is FFT instead of DFT. So here we have some data. Using DFT we have calculated its x of k. Now we want to use FFT instead of DFT to calculate these data. For this we are going to separate even and odd indices. That means our x of even will become 2, 3, minus 2 and 3, and x of odd will become minus 4, 1, 0 and 1. So here we separated it. This is x of even and this is x of odd. Now we are going to introduce a new term for simplicity, that is Wn. Wn is equal to e of minus j to pi divided by n. Now we will learn how we can use it. So when we put it in here in the DFT equation, we get x of k is equal to summation 0 to n minus 1 x of n omega n into nk. After that, okay, now we want to know what that omega n k is, what it is exactly is. To get the idea of omega n, we do this example. So here we let that our n is equal to 4. Then we will divide our circle in 4 parts. Here I have divided this circle in 4 parts. I have introduced that circle previously to you. So then for the first, let's say we want to calculate. So now our k is 1. So here k will be 1 and we will only be be left with n. So now for x of 1, that means xk is equal to 1. We have x of 0, x of 1, x of 2 and x of 3 as we do our iterations, like the summations, sorry. So here first of all n will be 0, then n will be 1, n will be 2 and n will be 3. Now w of 4, 0, what is this? This is w of 4, that means this circle and the position 0. That means the position 0. That means in place of w and 0 we will have a 1. After that w41. W41 is the circle for 4 and 1 is in clockwise motion, this position is 1. So w and 1 will be minus j. So you can see that minus j. And then w42 will be this position, and in place of w42 we will have minus 1, and w43 is this position, and in place of w43 we will have a j here. So this is all about w and k. We will have a fixed value for k and we will put it before, and then in the summations we will keep changing the values of n. And then from this circle, if we have, let's say if we have n is equal to 8, our circle will be divided into 8 parts, and we know these values 0.707 j and blah blah blah. I have introduced those values in the previous lecture. Okay, now so we have a formula to solve this problem. As I have mentioned that I have broke the series into even and odd terms. So I have got new formula that even values in terms of like we will find x of 1, 2, 3, 4, and odd values there also we find 0, 1, 2, 3, and there is a term wn of k. We will use this formula. First of all, we will find even indices and odd indices, means we will apply DFT on even indices and DFT on odd indices, and then we will multiply this term and add these two terms and we will get x of k. So let's check for this formula. Now first of all we will find it for the even terms. So even terms were let me check what was the even terms were 2, 3, minus 2 and 3. So now first of all we need to find x of 0 for the even term. X of 0 will be 0 from 0 to 3 because we have 4 terms only, so our n will be 4. 0 to 3, x of n, wn and 0k. 0 because our k now is 0. So we will get all will be 0, so all the terms will get added. 2 plus 3 minus 2 plus 3, so that is 6. For x of 1 we will have 0 to 3, x of n, wn and k. X of 0, wn of 0. That was 1, okay. X of 1, wn of 1. X of 2, wn, sorry I have not written 4 here, and 4 of 2, wn 4 of 3. And I have told you the way in which we can find all those values. Here's that way. So now we need to find 4 for 1. 4 for 1 here is minus j, so here it is minus j. Then 4 for 2 is this place, so here it is minus 1, so minus 1 here. And then 4 for 3 is this place, and that in this position we have j, so in this place we will have a j. This value will cut down with this, and we will add these two values and we will get a 4. So next iteration, here is the next iteration. We need to find x of 2. X of 2 is 0 from 0 to 3, x of n, wn, and now in place of k we have 2, here it is n. Then we need to we will do like x of 0, x of 1, wn 4, 4, 4. Okay, so 4 of 2, you know this value. 4 of 4, you don't know this value. 4 of 4 is basically we will move back to the circle, in the circle. That means if we have this circle, this position is 0, 1, 2, 3, and its value is 1, its value is minus j, its value is minus 1 and its value is j. So moving in a circle, this will be 0, 1, 2, 3, this position will become 4, 5, 6, 7, 8 and we will keep moving inside. So here we can see that 4, 2 is this position, so I have put a minus 1 here. Then 4, 4 is this position, so I have put a 1 here. And 4, 6 is this position again, so I have put a minus 1 here. We'll solve it and we will get a minus 6. Okay, then we will find x of 3. For x of 3 we have 0 to 3x of n omega n, and in place of k I have 3 here. Okay, then I have not written that expression here, you can find it because you are now familiar with W4, 1, 2, 3, 4, 5, 6, 7, 8, 9 and so on. So I have just put in the values in here and I have got a 4 here. Okay, I will do all of these things, all of these same things for odd values of n. So what were the odd values? The odd values were minus 4, 1, 0 and 1. Okay, now we will do all of these things for odd values, just like we will find x of 1, x of 2. You will find these values by yourself. Okay, so x of 1, x of 2, x of 3 and x of 4. Now we are going to test our formula, and the formula was x of k is equal to a of k plus omega n k b of k. So for x of 0 we will have a of 0, the even value, and then omega nk. Omega nk here, what is omega nk here? First of all I will tell you. Now n is equal to 8. Why? Because we are now joining even and odd values, and this position it will be 0, so this will become omega 8 0, and omega 8 0 is what? We will put on a circle in here, or I think I have that circle. So is that circle in which we have 8 partitions, so we can use it here. So omega 8 0 is this position, so its value is 1. So here I have put a 1, and I should write those terms in here for even and odd. So the even values that we have found are 4, 6, minus 6 and 4, and odd values are minus 4, minus 2, minus 4, minus 6 and minus 4. Okay, so now we are going to use these values here. So a of 0 is sorry, I wrote the wrong values. So now I have a0 is 6 plus 1 from the position, and then b0 is minus 2, so when we add it we get a 4. Same goes for x of 1. Here a of 1 plus a w8 1 and b of 1. So here we can take value of 4 and minus 4. Here it is 4 and minus 4, and this value is w8 1. This is w8, and the first position is this position, and we can take this value. So I have taken this value and then multiplied it and added it, so I have got 1.172 plus 2.828. Now we can confirm that x of 1 is x of 0, we have got x of 0 4 and x of 1 this value, and what we have got in the previous side when using simple DFT, we have got x of 0 is equal to 4 and x of 1 is equal to this, so we are getting same values in there and in there. So we wanted to verify the formula that we have wrote this graph, and then the position 2 is this, and its value is minus j. So we have used minus j here, and we have got minus 6 plus 6j, and it verifies this position. X of 2 was minus 6 plus 6j, and we have got minus 6 plus 6j. Now you will find x of 3, x of 4, x of 5, x of 6 and x of 7 by yourself, because you know the formula and you also know the answers. The answer will be same like this. So now we are going towards something else. We wanted to reduce the multiplication, so now we will try to look at how many of them we have reduced. So in this case now we had reduced our n to 4 because we had separated even and odd values. So here addition, the formula for additions were n into n minus 1, so we will get 12 additions. Previously we had how many additions? We will look at that. So we have got 12 additions and 12, 12, 12, 12, because 12 for even, 12 for odd, so we have got 24, and these 8 additions are extra. What are these 8 additions? These 8 additions are these additions: 1, 2, 3, 4, 5, and from 0 to 7 we have got 8 more additions, so these are 32 additions. And when we were using DFT, we had n is equal to 8, and we had 8 into 7 is equal to 56. So we have reduced from 56 to 32 additions. So the additions have been reduced, but our main focus was reducing the multiplications. So here we have n is equal to 4, so 4 का square is equal to 16, and then we know that we have done 16 multiplications for even and then 16 multiplications for odd, so we have got 32, and then just like this we have done 8 multiplications, because here we have multiplied these two terms, then these two terms, then these two terms, and so on. So we have got 32 plus 8 is equal to 40 multiplications, and previously when our n was 8, it was square of 8, and that was 64. So from 64 we have reduced to 40 iterations, 40 multiplications. So we are doing a good work that we have reduced from 64 additions to 40 and 56 additions to sorry, we have reduced from multiplication was 64 to 50 and 56 to 34 additions. So we are accomplishing our goal, and we can do more and more simplifications by doing more and more simplification. Just like we have reduced it into even and odd, we can do it like we can use the even terms and then separate the even terms in more even terms and more odd terms, and just like doing this, I have an example for these two. Here we are now using 2-point DFT. What is that 2-point DFT? You can see that we had even terms of 2, 3, minus 2 and 3, and minus 4, 1, 0 and 1. We can do a next stage for it. For even terms, we can again use even terms. Just like this, we will do 2 and minus 2. Odd terms will be 3 and 3. For this thing and for this thing, we will have minus 4 and 0, and then 1 and 1. So we are using this thing here. You can see that we have 2 and minus 2. Here we have 2 and minus 2, then 3 and 3, then minus 4 and 0, and then 1 and 1. So now what we will do all of those. We will apply this formula for actually. Now it will become x of k is equal to 0 to 1. Why 0 to 1? Because now we have just n is equal to just 2. This will be 0 to 1. X of n, w of 2, k n. So just like we had reduced some in the 4-point DFT, we call it the 4-point DFT when we separate our even and odd terms. Now we are separating it more and more, and we are simplifying it more and more. You can do it by yourself. First of all, you will find for these two terms you will find this thing. For these two you will find this. For these two you will find this. For these two you will find this. And after that, what you will be doing that. So we have found that for these two values, for these two values 2 and minus 2, we have applied those formulas, and we have found that we have got 0 and 4, and for these two we have found 6 and 0. Now these are even terms and these are odd terms. We are again going to use that formula, a of k plus w and k b of k. By using that formula, what we will get here, this is a of k 0 plus this is b of k 6 and w 4 of 1 will be 1, so I'll use 1 here and this will become 6. Again for this term it will be like this, and for this term it will be multiplied by like this, and it will be multiplied like this. So we are using again using these formulas, applying these formulas and finding out our values. After this you can see this thing also we have used these two things, and one another thing, we have simplified this thing this much that now we don't need to use that exponential terms. We will just add these two and we'll get this. We will just minus these two and we'll get this. So here you can see that 2 minus 2 is 0 and 2 minus 2 is 4. Here 3 plus 3 is 6 and 3 minus 3 is 0. Here minus 4 plus 0 is minus 4 and minus 4 minus 0 is minus 4. Here 1 plus minus 2 and 1 minus 0. After that means in this step you don't need to do multiplication, you are just doing additions, and after that you will multiply, you will have those minor multiplications from this thing. So after all that we can conclude that in terms of additions we are just left, we had n is equal to 2, so we are left with 2 into 1, and then we had done 4 iterations. So for the 4 times we are multiplying it with 4, so we have got 2 plus 4 is 8. And why 8 plus 8? Because we are doing it for evens and then odds. Okay, so this is 16, and then the last multiplication that we have included previously, that is plus 8. So you can see that we had started from 56 and now we are at 24. We have reduced our additions more and more, and in the multiplication section you can see that there is no multiplication, this is just addition. So from here we have 0. Then this 8 is from these multiplications, and at the end the last one 8 is that last one 8 that we will be doing on these terms and these terms, and then using that even and odd formula. So this 8 is from that. So we are now at 16. We started from 64 and now we are at 16. So we have reduced our multiplications significantly. We started from O n and we are now at O n log 2 of n. That is significantly very good. So we are done with our task. Our task was to reduce cost, and how the cost will be reduced when the multiplications will be reduced, and you can see that we have reduced our multiplication. And the other thing we wanted to reduce was this worst case. First of all we had our worst case as 0 and now we have our worst case as n log 2 of n, and this value is much greater than this value. So we have successfully reduced both the things, and we are done. That's all for today's lecture. For more amazing videos like this, keep watching our channel Digital Signal Processing. Thank you. Lanat.